Good evening, everyone, and welcome to the ninth problem-solving session of the course Computational Continuum Mechanics. So I'm Naresh. I'm a research scholar in the Department of Civil Engineering at IISc. So today the focus of our discussion will be constitutive models, a little bit of constitutive modeling, and then we'll quickly get into the hyperelastic models. So that is what the assignment for this week is based on. So we'll solve some hyperelastic models, some problems on hyperelastic models. And then we'll also look at some boundary value problems. So the first, let me quickly revise what the idea is. Uh, So we can start with the various kinds of materials that are possible. So in the last session, we saw why constitutive relations are required. Constitutive relationships. So last time we saw the number of with only equilibrium, stress strain. Sorry, stress strain is the strain displacements. And the first law and the second law of thermodynamics, we saw that we have more unknowns than equations. We had more unknowns than the equations. Therefore, we wanted additional conditions, and that is given by, and these are all physical principles. They are not, they are common for all the materials. So also conservation of mass. So the conservation of mass, equilibrium, which is the conservation of linear momentum, first law, second law, and the strain displacement, that is F is equal to grad phi or grad x. So these are not really enough to solve for all the unknowns. We saw that we had more unknowns than equations, and these are to be satisfied by any material on Earth. So so there is nothing specific to material properties here. Therefore, we need certain additional conditions for closure of the system. And this closure is brought about by constitutive equations. So materials can be classified depending on the type of constitutive model. So in general, and there, in addition to this, there also there are certain restrictions on constitutive models as well. And this was also covered last time. So we said that they should be the first principle is principle of determinism. Just a minute. So the first principle is principle of determinism, which says only the events in the past and the history of deformation can affect the events, the current state or the future. So the current relationship, the constitutive relationship, cannot depend on the deformation gradient or the temperature in the future. So only past affects present, That is logical. The second thing is locality, which says the stress at a point depends only on the deformation history of that point. So stress at a point depends only on the deformation history at that point, at the same point. So the stress somewhere else cannot affect this deformation somewhere else directly. Then the third thing was frame indifference. So this the equations of all our governing equations have to be frame indifferent. Not only that, the constitutive equations have to satisfy a certain condition called material frame indifference. Material frame indifference. So these are the conditions to be satisfied by any constitutive relation. But further, so these are in general. These are to be satisfied regardless of whether it's a solid or a liquid or any continuum for that matter. So yeah, so this part was fine. And if you look at the hierarchy of materials, so the broadest category, the broadest category that satisfies all these three are the class of local, history dependent, aging material. So I can categorize this as say M1. And okay, another related concept here is the concept of response functions. So I can also tell that. So we need something called something called response functions. What are response functions? So suppose we have the Cauchy stress sigma, and you want a relationship between sigma and say uh, the left Cauchy green tensor B. Right. So suppose we wanted a relationship between these two for as a constituent for closing this system of equations. Right? So we have a lot of unknowns here. Suppose we wanted a relationship between these two. Then in general, this is a mathematical quantity, which is stress. This is a mathematical quantity, which is the left Cauchy green tensor. Green tensor. The relationship between these two is given something like this. Sigma is a function of the point where we are looking at and this one. Right? So this is a quantity. This is the point. This is the material point. So the constitutive relation can be different at different material points. And this is the kinematic quantity or the strain quantity. Right. So this is the left Cauchy green tensor. This is the stress. This is the Cauchy stress. And the relationship between these two is given by some mathematical function. And this function is the response function. So the response function for a certain physical quantity, I'm denoting by a small cap on top of it. So this is a function which takes in some value and returns some other value. This is the value it returns, and this is what it takes in. So now let's look at the class of materials M1. Make it blank. Let's look at this class of materials M1. And what is special about this? So it is local, it is history dependent, and aging. So in this category M1, the response function is in general given as suppose I want to relate the first PLR Kirchhoff stress tensor with its work conjugate. With its work conjugate. What is its work conjugate? It is the deformation gradient. So diff grad. So the first Piola-Ketkoff stress tensor, which varies with the point where we are looking at, the material point, and also at which instant of time we are looking at. This is a function of what all? It can depend on time. The constitutive relation can depend on time. It can depend on, it can vary from one material point to another material point. So material can be non-homogeneous, and then it depends on uh, the deformation gradient. But it is history dependent, so it depends on the deformation gradient all the way from, so at the same point, so it is local, therefore it cannot depend on the deformation gradient elsewhere, so it depends only on the deformation gradient. So this x is the same as this x, right? So this means the constitutive relationship is local. So if it depends on some other point y, which is not equal to x, then it means the constitutive relationship is non-local. So for a majority of the engineering materials are local materials. They have local constitutive relationships. So it depends on the deformation gradient at the same point, but it is history dependent. So it depends on the history of the deformation. So the time instant can actually be different. It doesn't have to be s. It can be some time s less than or equal to t. It can be any time s less than or equal to t. So this response function actually takes in all the entire time history from s equal to say minus infinity, which is very far in the past, up to the current time instant t. So this is the notation. So p cap represents the response function. It takes in the time, the current time, the current material point location, and it takes the entire deformation history from s equal to minus infinity, which is very far back in the past, to the all the way up to the current time t. So this is a local history dependent aging material M1. Now let's look at another category M2, which can be local. Again, it is local. It can have history dependent. But simple material. So simple in this case, it means not aging. So what do we mean by not aging? And the material is not aging. So in this case, there is no explicit dependence of the constitutive relationship on the time. On time. Therefore, the dependence of P on T comes only through F. So it's like P at any instant at any given material point X is given as P cap of. There's no dependence on T. Therefore, if you do an experiment with a certain deformation history, either now or later, if the deformation history and the material point are fixed, no matter at which point we are carrying out the experiment, it will give the same stress response. Unlike certain polymers called aging polymers or biological materials, which give a different stress response depending on which time. So subjected to the same deformation history, they can give two different stress responses if it is an aging material. But if it is a simple material which does not undergo aging, then it is the response function is something like this. It depends only on the material point where we are measuring it and the deformation history of that material point. So S is any time before t. So it's like S going from minus infinity to t. So this kind of relationship categorizes a simple material. So the response function depends on the entire deformation history of that particular material point, all the way from very far in the past up to the current instant. However, the form of the constitutive relationship does not depend on time. Its dependence on time is only through the dependence of the deformation gradient on the time. Third type of, so this is M2. Now let us look at the third type of material, which is simple elastic. Now I can call this M3, which is simple elastic materials. Simple elastic materials. Okay, so now, so when we say elastic, it is no memory. The material has got no memory. So no matter what kind of deformation histories it has got, an elastic material, the response of an elastic material is instantaneous. So the suppose we have a simple elastic material. The stress in the material at any given material point and the time depends only on the material point which we are looking at and deformation gradient at the material point in the current instant of time. So contrast with the other cases, here we have an S which is less than or equal to t. So the entire deformation history, f of x comma 0, f of x comma 1 second, f of x comma 2 seconds, the entire deformation history gets into the constitutive relation. Unlike that case, here there's no S, it's only the current t. So no matter how we have got to the current state of deformation, the response is always on the current deformed configuration and not the history of deformation. So this is a history independent material. So elastic materials are history independent and they have got no memory. So this is the third class, which we this third important class. There are many other varieties. So this is a simple elastic materials. Then you can have another class of materials, say called hyperelastic materials. You can have another class of materials called hyperelastic materials, which in addition to being elastic, in addition to being simple elastic, they have the additional constraint of so existence of a stored energy function. So existence of a stored energy potential means the stored energy function, the internal energy, is a function only of the strains. So it's either strain energy or stored energy. It's a function only of the deformation at the current instant. So it depends only on f of x at the current instant at any point. So let me use the usual notation. So it's like this is the stored energy function at any material point given the current deformation state is what? It is integrated from the starting point time t is equal to t naught to the current instant. So here this is the response function. I should put a cap. It's the so this you know that the you can use any work conjugate pair here. So it can either use the first Piola-Kirchhoff stress tensor and the deformation gradient, the second Piola-Kirchhoff stress tensor and the Green-Lagrange strain tensor, or the Cauchy stress tensor and the rate of deformation tensor. So let's use the first Piola-Kirchhoff stress tensor. We know the first Piola-Kirchhoff stress tensor in general for a simple elastic material, it depends only on x and f of x comma t. this is inner producted with f dot of x comma t dt. So t going from some time in the past to the current instant. So this is the work done by the external forces or work done by the internal stresses over a period of time t naught to t finals. And this, so since it is integrated over time, the result has to be independent of time, and we go have what is called the stored energy function, and that depends only on the current state of deformation. So this integral exists, and under certain conditions, this is also path independent. So when it is path independent, we don't really this can be defined beforehand. So for hyperelastic materials, this function can be defined beforehand. This can be defined. So conversely, once you can define a stored energy function, it is possible if you look at the derivative of the material time derivative of the stored energy function, what it is just remove the integral, whatever is inside is the material time derivative. It is just t double dot f dot, right? But you also know that this is d psi by dt, and psi is a function only of psi at a material point is a function only of x and f of that material point at that instant of time, because such a function exists. It is hyperelastic. Such a function exists, and it is possible to it is differentiable. We assume it is differentiable. So because such a function exists, using Taylor series or using chain rule, you can write it as dou psi by. So it depends on x, but x is the material point. Everything is happening at a material point. So we are not. This is a material time derivative, right? So this is the material time derivative. Which means x is held fixed, which is the material point is held fixed. So this will not change. The variations are only in the deformation gradient. So it is the partial derivative of psi cap, which is the response function of the stored energy stored energy functional, with respect to the deformation gradient f, inner producted with the material time derivative of f with respect to, yeah. So this is a tensor, this is a tensor. So in initial notation, you can say it is dou psi. Psi is a scalar divided by dou fij and dfij by dt. So comparing these two equations, what we get is that, so we get psi dot is equal to p double dot f, which is also equal to dou psi by dou fij dfij by dt. And this also can be written in initial notation, which is nothing but pij f dot ij, and this nothing but f dot ij. So take it to the left hand side, you get minus dou psi by dou fij f dot ij is equal to 0. Now say now you invoke the arbitrariness of fij dot, so we get pij should be equal to dou psi by dou fij, because fij dot can be arbitrary. So for a hyperelastic simple material, for a hyperelastic material, or it's a green hyperelastic solid, it's also known as that, the stress is derived as a derivative of a scalar potential. And equivalently, you can also say the second Piola-Kirchhoff stress tensor Sij is the derivative of the stored energy function with respect to the green Lagrange strain Yang. So these are the relationships in indicial notation. Okay. So we have defined hyperelastic solids, so I can go to the next step. Now, a special case of hyperelastic solids is isotropic hyperelastic solid. So when we say certain, so isotropic means the correct definition of isotropic is that the material symmetric group, the material symmetry group contains all proper orthogonal rotations. That is, contains the entire set of. So let me define what is material symmetric group. So material symmetric group is a group. So group is a set plus an operation. So for example, if you look at the set of all orthogonal tensors along with the tensor product operation. This set of all orthogonal tensors with the tensor product operation forms a forms a group, right? This forms a group. Let us call it G. So if you take two, and so this set can be called, say, this G, and this operation can be called, say, a star. So if you take so this is called a group when you take two elements of this set G and then you operate on them, and that operation has to be associative. So it's like A star B star C should be equal to A star B star C. This is the first condition. The second condition is so for it has to be associative. Then there should be a neutral element. There should be a neutral element. So a neutral element is, let us call it N. So A acting on N should be equal to N operated on A should be equal to A. So this is called the condition of the existence of a neutral element. And the third thing is there should be reverse element. So it's like there's an element A reverse when acting on A, and when A acts on A reverse, it gives the neutral element N. So this when these conditions are satisfied, this is called a group. So we say group is a set of something. It could be a set of any objects. It could be a set of tensors. It could be a set of operations. It could be a set of even numbers, right? And the operation can also be anything that we call. So operation can, in this case, I'm looking at the set of all orthogonal tensors along with the tensor product operation. So is this a group? Yes. You take two orthogonal tensors and do a tensor product of them. The resulting tensor is also an orthogonal tensor. So that is one thing that also lies the set. Therefore, it is closed. So so for all this to hold, it has to be closed. So closure property is also important. So you take two elements of the set, do this tensor product do this operation, star operation on them. The result has to be lying in the same set G. Then it means that operation is that set is closed. So only if it is closed, we can do all these operations. So if it is closed, then you look for these three conditions. So you look at A operated on, B operated on C. So we can check all these for orthogonal tensor. Let us say Q1, Q2, Q3 are orthogonal tensors. So is it closed? Can we check if it is closed? And the operation star is tensor product. And the set G is set of all orthogonal tensors. Now look at the group G comma star. So is this group closed? So let us say Q1 star Q2. What it is? It is just Q1 Q2. If it is orthogonal, what is the condition? The condition for orthogonality is let us call this one, say, Q3. Okay. So if a tensor is orthogonal, then we know it is Q transpose Q should be equal to the identity, right? It has to be equal to the identity. So what is Q3 transpose Q3? it is Q2 transpose. I'll do it step by step. So Q3 transpose Q3 is Q1 Q2 the whole transposed Q1 Q2, and which is equal to Q2 transpose Q1 transpose Q1 transpose Q2 transpose, which is also equal to, these two will together give identity. So it is Q2 transpose identity Q1 Q2. Let me write it clearly. So this will give identity. So it is Q2 transpose I Q2, and this is nothing but Q2 transpose Q2, which is I. So so the product of these two, is also orthogonal. Therefore, it is closed. What is the second? If it is closed, then we'll check the three conditions for a group. So what about this? So this is Q1, Q2, Q3. What this is? It is that Q1 star Q2, Q3. This is Q1, Q2, Q3, and this is also equal to Q1, Q2 star Q3, which is Q1 star Q2 star Q3. Therefore, this is associative. So first condition is satisfied. What about the second condition? Existence of a neutral element n. Now, is there an operation such that n star q is equal to q for all q? Is there such an operation? Answer is yes. What is it? It is the identity tensor. Is the identity tensor. Let us call the identity tensor this bold one. Let's call it bold one. Or let's just call it I. It's easy. Let's call the identity tensor I. So we have an identity tensor. We have a neutral element because IQ is equal to QI is equal to Q. Therefore, the neutral element for this group is I. So this second condition is also satisfied. What about the third condition? Third condition is existence of a reverse. So it's actually an inverse. In general, for groups, we call it the reverse. So do we have a reverse? Yes. So Q transpose Q is I, which is N. So Q transpose Q is nothing but Q transpose operating on Q is equal to N, which is also Q transpose. Therefore, there is a reverse, and the reverse operation is nothing but transpose. So the third condition is also satisfied. Therefore, the group of all orthogonal tensors along with the tensor product operation is a group. Now, what is a material symmetry group? So for given a material, is there a group? Right? If a group, so what is a symmetry group? Symmetry group is the group of transformations that can be applied to the reference body leaves the material response unchanged, right? So what it means is that you have a body, say this is the reference body B0. We are applying some transformations on the material body. Let us call the transformation small g. So it could be something like a rigid rotation, right? It could be something like a rigid rotation. And then we are subjecting it to the deformation F. So this is some other transformation F. So this deforms to some form. Now you can also go directly to this by how? So if this is G, this is F. F is applied on G, so it is actually F composition G. And this is the current body. So you're going to the reference body. This is the transformed reference body. I can call it B0 T or something. And this is the current body. So the stresses are all in the current configuration. We know that, right? So this is the deformed configuration. This is the actual deformation. And at any point, so you have a point capital X here. So because of some transformation, that point goes to here, which is some other point Y. And you apply this small f on that, you get the deformed body. So what a symmetry, if G is a symmetry, if G is a symmetry transformation, then the material response in the deformed configuration should be unchanged. So what it says is, so these are the mappings, right? F and G are mappings, so it should depend only on the, so let me say, so the response function, so let's look at the Piola-Kirchhoff stress tensor and the deformation gradient, which form a work conjugate pair, right? Now, you can think of this as a reference configuration, and from there you're getting the deformed configuration, in which case P is equal to the response function of Y, comma, the gradient of F with respect to Y. So this is one response function. But you can also think of it as coming from the original body over which some transformation was applied. So then the stress will be P is equal to P. What is the original body before this transformation? It is X, and it is grad of F composition G. So using chain rule, so let us say the gradient of the deformation F is capital F, and the gradient of the deformation G is capital G. Now we are doing a composition. So the grad of F composition G using chain rule, it is nothing but Fg. So if G is a symmetry group, if G is a symmetry transformation, so symmetry transformation means you apply it onto the material body and the final response will be unchanged. So it's like we take a square and rotate it by 90 degrees. So the appearance is unchanged. But if you rotate it by 45 degrees or 100 degrees, the appearance will be changed. So rotation by 90 degrees is a symmetry operation for the square. So rotation by 90 degrees leaves the appearance of the square unchanged. Therefore, it's a symmetry transformation. Similarly, for the material, whatever transformation leaves the material response unchanged is a symmetry transformation. And the collection of all such symmetry transformations along with an operation constitutes a symmetry group. So the definition of a symmetry group here is that if G is a symmetry transformation, then these two stresses, which are obtained from these two different bodies, which are just related by a symmetry transformation, should be the same. Therefore, if G is a symmetry transformation, then the response of this thing, Y comma F should be equal to the response of X comma Fg. But if you see carefully, the material point itself is not changing. The material point is Y. We shouldn't change the material point. Sorry, material point is X. Under the operation of G, it goes to Y. And under the operation of F, it goes to some X of something, X of Y comma T. Or actually F of Y comma T. So the material point itself is not changing. Therefore, the response should not change. It cannot depend on the different material point. So P of Y comma F is nothing but the response of X comma F, because the X identifies the material point. Therefore, if G is a symmetry transformation, if G is a symmetry group, symmetry transformation, then P of X comma Fg should be equal to P of X comma F. So you see what this G does. So G acts on an infinitesimal vector and returns another infinitesimal vector, which is a different in the material space. And F acts on this infinitesimal vector and gives d small x, which is in the deformed body. So this is in the material body. This is the reference configuration. This is also a reference configuration, a new reference configuration, and this is in the spatial body. So G is an entirely Lagrangian tensor. Okay, so this is what the symmetric group does. So when do we call a material is isotropic? So isotropic is when the symmetry group G, let us say, if G is a symmetry group of the material. So by symmetry group, we mean the collection of all transformations which leave the material response unchanged, or the collection of all such small g's which obey this condition. P cap of x comma fg is equal to P cap of x comma f. The collection of all such transformations which leave the material response P cap unchanged, that is the symmetry group G, material symmetry group G, when this group contains the set of all orthogonal tensors, set of all rotations. So basically this means that you take the material, rotate it in any way you want, and in all the directions you get the same response. So that agrees with our usual definition of isotropy. So the properties are the same in all directions. That is the usual definition of isotropy. But we cannot define directions without an axis, without axis system. So this is the rigorous definition of isotropy. You look at transformations which leave the material response unchanged, construct a group called the symmetry group with these transformations. If this symmetry group contains the set of all rotations, all rigid rotations, then that material is isotropic. Material is isotropic. So clearly, a material that is isotropic does not have any. So isotropic material response does not depend on the axis. Directions, or rather it should not depend on which coordinate axis we are using. So so it has no preference, all directions are same at a material point, then that at that point the material is said to be isotropic. So if we have an isotropic function, if we have an isotropic, so when we say the material response is isotropic, what do we mean? We mean that get to this part. Yeah. Yeah. So given that, suppose we have an isotropic function. We have an isotropic function. Let us say we have a isotropic function of scalars, right? So if we have phi of a scalar s, right? If we have an isotropic function of a scalar s, then whatever transformations we apply to the argument of the function, it's going to return the same function. But a scalar doesn't have direction, so it is just phi of s. So this is trivial if s is a scalar. On the other hand, if we have a vector, if we have a function phi, a scalar function of a vector v. So if it is an isotropic function, then what? It has to depend only on, it cannot depend on the components of the vector as it is. So we have a vector. So we have a vector v. So this function takes in a vector and returns a scalar. And this function is isotropic, which means it doesn't depend on the directions. So therefore it cannot depend on both the components of the vector. It depends only on the magnitude of the vector. So it is like it has to. So if you apply any arbitrary rotation to the vector, it has to be equal to the unrotated vector because there is no direction for this function. So suppose if this scalar function, so this invariant with respect to rotations q. Okay, then what about tensors? So how do tensors transform? So an isotropic function of a tensor, it can take in, suppose it is S is a tensor, then no matter what orthogonal transformations we do to the tensor, it has to return the same. So for an isotropic material, for an isotropic point, for an isotropic material point, the entire set of rotations constitute the symmetry group, material symmetry group, which means if we apply any rotations onto the material point, the resulting response should not change. So what does that mean? It means that you take a scalar, you apply a rotation, we should get the same response. But you can't rotate a scalar because it has got no directions. Therefore, phi cap of s should be equal to phi cap of s, and s is a scalar. But what if we have a vector? You rotate the vector, you should get the same response as in unrotated case. So when is it possible? So it is possible when phi of q is equal to v for all. So this is when v is a vector and q is orthogonal rotations. Sorry, q is rotation tensor. Now similarly, if you have a tensor S, we know the tensors transform as q transpose. So if phi is an if phi is an isotropic function of a tensor, then even if we rotate the tensor to some other coordinate system, we have to get the same result. So the result of the function should be insensitive to any rotations q applied onto a scalar, vector, or a tensor. So here S is a second order tensor. So this characterizes an isotropic function. But when is this possible? So when can a vector be isotropic? So if there exists a function phi cap of v is equal to some phi tilde of only the magnitude of v, then phi cap is isotropic. If there exists a phi tilde, if you can write this phi cap of v as some other function which depends only on the magnitude of the vector v, then phi cap is isotropic. Why? Because the magnitude of a tensor, the length of a vector does not depend on which coordinate system we are using to describe the vector, right? So the length of a vector does not depend on the component. So the length of a vector is invariant to orthogonal transformations. We can rotate a vector and have the same length. Therefore, it if there is such a function, so suppose you rotate it, f of say qv is what? It is phi tilde of magnitude of qv. But what is magnitude of qv? It is square root of qv dot qv. And this is nothing but phi tilde of, use the property of transpose, square root of v dot q transpose qv, which means q transpose q is I. Therefore, phi cap of qv is equal to, we said it is phi tilde of magnitude of qv, and we said it is phi tilde of square root of v dot q transpose qv, and this is nothing but phi tilde of q transpose q is I, so it is square root of v dot v, which is magnitude of v. But what is phi tilde of magnitude of v? It is nothing but phi cap of v. So this function is insensitive to applied rotations q. Therefore, it is an isotropic function of a vector. Similarly, for tensor, so the length of a vector is an invariant of a vector. So the length of a vector is invariant. It's an invariant of the vector. It's invariant to rotations. Similarly, for a tensor, now suppose phi is an isotropic function of a tensor. Right, so let us say I1, I2, so let S be the tensor, and I1, I2, I3 be the invariants of the tensor. Right, so what are the invariants? Invariants are when you say determinant of S minus lambda I, you get a characteristic equation. What is the characteristic equation? The characteristic equation is lambda cube minus I1 lambda square plus I2 lambda minus I3. Right, so it could be plus or minus, right? So these are the coefficients of the characteristic polynomial. And if phi is an isotropic function of a tensor S, then there should be a function phi tilde such that phi cap of S is equal to phi tilde of the invariants I1, I2, and I3. How do we show that? We can see that because suppose we apply a transformation, S becomes Q S Q transpose. So we are rotating the tensor S. So we have S, we are applying a rotation onto the tensor S. You know, rotation of a tensor acts according to, say, Q S Q transpose is the transformation rule for a tensor. Now let us look at the characteristic polynomial of Q S Q transpose. So it is determinant of Q S Q transpose minus lambda I. So this can be written as determinant of Q S Q transpose minus lambda I can be written as Q Q transpose. Now look at the matrix inside. So it is, you can take Q and Q transpose commonly out. So it is determinant of Q S minus lambda I Q transpose. So this is basically determinant of Q, determinant of S minus lambda I, determinant of Q transpose. But Q is a rotation. We are rotating the tensor, so Q is a rotation matrix. Therefore, determinant of Q rotation matrices have determinant 1. And you have a determinant of S minus lambda I. And you have again determinant of Q transpose. So transpose doesn't affect the determinant, so it is 1. But what is determinant of S minus lambda I? It is the characteristic polynomial of the matrix, polynomial of the vector. Sorry, it is the characteristic polynomial of the tensor S. So it is lambda cube minus I1 lambda square plus I2 lambda minus I3. But by definition, this is also the characteristic polynomial of Q as Q transpose, because that is what we have on the left hand side. Therefore, the first invariant of, and it has got the same coefficients as S. So the first invariant of Q as Q transpose is the same as the first invariant of S. The second invariant of Q as Q transpose is the same as the second invariant of S. And the third invariant of Q as Q transpose is the same as the third invariant of S. Therefore, if we apply orthogonal transformations, if we apply an orthogonal transformation onto a tensor S, the invariants remain unchanged. That's why they're called invariants. Therefore, a function phi is said to be a function phi of a tensor S is isotropic. So this is isotropic if and only if there exists a function p tilde such that P of S is equal to phi tilde of the invariants of S, I1 of S, I2 of S, and I3 of S. So we know that the invariants are not affected by orthogonal transformations, which implies phi cap of S is equal to phi cap of QS Q transpose, because QS Q transpose and S have the same invariance. So the forward part of the proof is easy. That show if the if it is a function only of the invariants, then this always holds. But to show the converse, suppose we have two tensors A and B with the same invariants. So if they have the same invariants, it means they have the same characteristic polynomial. So if they have the same characteristic polynomial, it also means they have same eigenvalues. But the tensors themselves are different. Therefore, so if A and B are tensors with the same invariants, invariants are the same as the coefficients of the characteristic polynomial are the same, which means their eigenvalues are also the same. But the tensors themselves are not the same in general. Therefore, the eigenvectors have to be different. So by spectral, if A and B are symmetric, so if you assume A and B are symmetric, then A can be written as a sum of its eigenvalue 1 multiplied by E1 tensor E1, eigenvalue 2 multiplied by E2 tensor E2, and eigenvalue 3 multiplied by E3 tensor E3. where E1, E2, E3 are these are the eigenvectors. E1, E2, and E3 are the eigenvectors. Similarly, B will be same eigenvalue, E1 star tensor E1 star, and lambda 2 E2 star tensor E2 star, and plus lambda 3 E3 star tensor E3 star. So they have the same eigenvalues and different eigenvectors. But these E1, E2, E3 and E1 star, E2 star, E3 star constitute an orthogonal system. E1, E2, E3 forms an orthonormal system. E2, E3, E1 star, E2 star, E3 star form an orthonormal system. Therefore, two orthonormal systems can be rotated by some related by some matrix Q, and that implies A and B are related by the same matrices. So simple. So therefore, B is equal to some QA Q transpose. So the eigenvectors can be related by some orthonormal relationship. They have the same eigenvalues. Therefore, each of the basis vectors. So E1 star tensor E1 star is some Q E1 tensor E1 Q transpose. E2 star tensor E2 star is equal to some Q E2 star E2 tensor E2 Q transpose, and E3 star tensor E3 star is some Q E3 tensor E3 Q transpose. Now you can take Q and Q transpose commonly out. Therefore, we get some B is equal to QA Q transpose. Since now since since two tensors with the same invariance, say for example, let us say S1 is one tensor, S2 is one tensor, but they have the same invariance, I1 of S, I2 of S, and I3 of S. So suppose phi tilde of S1 is equal to some its invariance. Say I'll use the stylish I. So I1 to 3, and phi of S2 also has the same invariance. Then S1 and S2 should be related by a rotation, a rigid rotation. Therefore, S2 should be some QS1 Q transpose, which means phi of S is equal to phi of QS Q transpose. Therefore, if the functions depend only on the invariance, then it is isotropic. So the first part is if the function is isotropic. So if the function is isotropic, then yeah, if the function is isotropic, then it has to then it depends only on the invariance, not the tensor itself. And if there is a function that depends only on the invariance of a tensor, then it is an isotropic function. So both the sides we have seen. Now we are looking at isotropic hyperelastic materials. So we are looking at isotropic hyperelastic materials. So when it comes to isotropic hyperelastic materials, first thing, it is hyperelastic. So therefore, there exists a stored energy function. Sorry. So there's a stored energy function C of x comma f of x comma t is some response of. So you can draw. So suppose one more thing. So this is the stored energy function. Now suppose it is homogeneous. We can drop. There is no explicit dependence on x. So if the stress strain response at every point is homogeneous, so the stress strain response is independent of which material point on the body we are looking at, then it is the body is said to be homogeneous, not the material. The body is said to be homogeneous if every material point of the body has the same response function. So this means it is just it depends only on the deformation gradient and nothing else. So this is a homogeneous isotropic hyperelastic material. So if it is isotropic, then the psi can depend only on the so psi is some psi of let us say the right Cauchy Green tensor, and if it is isotropic, it can depend only on the invariance of the right Cauchy Green tensor. So for a general, so this defines an isotropic hyperelastic material. Now let us look at the properties of an isotropic hyperelastic material. So let us start with some problems. So let us start with some problems for today. Right. So I'll put it in as we do the derivation. So first thing, so we have a material whose stored energy function is given as it's isotropic and hyperelastic. So it is something like psi1 of I1, I2, and I3, which are the invariants of the these are the invariants of the right Cauchy Green tensor C. Now using the chain rule, we can using the chain rule, we can. So in the last session also we did this. In the last session we saw that half S colon C dot. So this gives an internal virtual work, which means S is equal to 2 times dou W by dou W internal with respect to C. And in terms of the stored energy function, when the internal virtual work depends only on the stored energy function, it is S is equal to 2 times dou psi cap with respect to C. Now what is dou psi cap with respect to C? Here we can use the chain rule. It is nothing but dou psi cap with respect to the first invariant. So this is a scalar, but the result has to be a tensor multiplied with dou I1 with respect to dou C plus dou psi cap with respect to the second invariant, a partial derivative of second invariant with respect to C plus dou psi cap with respect to the third invariant and dou I3 with respect to C. Now the particular form of the function psi1 psi will determine psi of so these will be determined by the particular form of psi. But the second whatever is multiplying them can be found in common. So let us see what I1, I2, I3 are. I1 is what? I1 is the trace of C. I2 is half of trace of C square minus, let me check that. This I2 is half of trace of C the whole square minus trace of C square. And the third invariant is determinant of C. Now let us look at, now we need to let us find these derivatives. Right? So the first step, let us compute the partial derivative of I1 with respect to C. So what is I1 in terms of C? I1 in terms of C is CKK. So it is the sum of the diagonal entries of C in any component, right? So that is it. Then this is a derivative of a scalar with respect to a tensor. So in Cartesian coordinates, you can call it dou I1 with respect to dou Cij, EI tensor Ej. So this is nothing but dou I1 with respect to dou C. But what is this? This is nothing but dou by dou Cij of CKK, EI tensor Ej. So now what is dou CKK with respect to Cij? So this is so when k is equal to I and yeah, so this is delta. So this this is 0 whenever I and j are not equal, and it is, so this is delta ki delta kj ei tensor ej. And this is basically ek tensor ek. What is ek tensor ek? Ek tensor ek is e1 tensor e1 plus e2 tensor e2. So it is like e1 tensor e1 plus e2 tensor e2 plus e3 tensor e3. So by spectral decomposition theorem, what are the eigenvalues? All the eigenvalues are equal to 1. So which is the tensor with all eigenvalues 1? It is just the identity tensor. Therefore, dou I1 with respect to C is nothing but the identity tensor I. So this is done. Then the second invariant, let us look at the derivative of the second invariant. So dou I2 with respect to C is nothing but half of dou by dou C of trace of C the whole square minus trace of C square. I use the chain rule, so we get half of this. If you apply the chain rule, you get this is a scalar with respect to a tensor, so it's 2 times trace of C multiplied with dou trace of C with respect to C minus, here we have trace differentiated, so again it is dou by dou C square, so dou trace of C square with respect to C square multiplied with or rather, let me do it this way. So I'll keep this as dou by dou C of trace of C square. So in the first term, dou trace of C by dou C, we already found it is the identity tensor. So the first term is nothing but, so 2 gets cancelled. It is trace of C to I minus, in the second term, let us use the indicial notation. You have dou by dou Cij of trace of C square. So it is, what is C square? C square is, so we cannot use I and j. So let us use CPM CMQ EI tensor EJ. And there is a half. So this is the second term. So therefore, this result is trace of Ci minus half of, I use the chain rule. Now all the differentiations are with respect to a scalar Cij. So so it is dou by dou Cij of, what is this? This is the pqth component of C square So PQ trace of C is just contract P and Q. So we get trace of trace will just contract and return a scalar. So we get dou by dou CG of dou CPM CMP EI tensor EJ. But what is CPM CMP? C is a symmetric tensor. Therefore, C is equal to C transpose, which means CPM is equal to C transpose PM, which is equal to CMP. Therefore, CPM and CMP are the same. So this is nothing but CPM squared. So we get trace of C I minus half dou by dou Cij of CPM CPM. So differentiate, so use the product rule and then use the property of this. So we get trace of C I minus, so this half and the 2 that we get by differentiating this will get cancelled. So we get a CPM delta PI delta MJ EI tensor EJ. So this EI tensor EJ is here as well, EI tensor EJ. So delta has the replacement property. In place of P replace I, in place of M replace J. So we get trace of C I minus Cij EI tensor EJ. So but Cij EI tensor EJ is just C. Okay, so this is the derivative of I2 with respect to C. Now the third so the third part is, let us say, differentiation of I3 with respect to C. So I3 is nothing but the determinant of C. So it is dou by dou C of determinant of C with respect to C. Now this is not straightforward. If we use indicial notation, we'll get into some very big expression. So so let us directly using the indicial notation is going to make it very long. So let us do something else. Suppose we have a certain function. Suppose we are interested, so say let us say we are interested in the material time derivative or time derivative of determinant. Suppose we are interested in the time derivative of determinant. You can say it is d by dt of dit C. What it is? It is dou by dou C of dit C double dot product with dc by dt. So this is what we have right now. This is what we have right now. Okay, so now suppose we have we are interested in the determinant of some determinant of C plus. So suppose we are interested in so it's like we are in a small time instance. Say you go from t to t plus delta t. How does C change? That's what it means. So so you go from C to C plus h times s, where s is any tensor. So it's so the left hand side is basically C determinant of C plus hs divided by h in the limit h tends to 0. Right. So let us first see what this expression is. So this will be determinant of C plus the directional derivative of C in the direction S. Right. It is the directional derivative of C in the direction S at the point 0. let me denote it by D. Let me just check the. Yeah, so suppose H is a small parameter. It is, take H as a small parameter. S is the direction in which we are perturbing C. So what we'll have is, here we'll have the directional derivative of determinant of C in the direction U, in the direction S. And H will also multiply this. So this is what it is. So let us see what this factor is, right? So what is this factor? We'll see that. So now consider this determinant of C plus Hs. So this can be written as determinant of C multiplying I plus H is a scalar. So H is a scalar and S is, so we have a C which is pre-multiplying. So we have a C inverse S, right? So what we are trying to do is we are trying to derive this using some Taylor's expansion or something similar from det C. So what it is? So determinant of a product of two tensors is the product of the determinants. It is det C multiply det of I plus H C inverse S. Okay, so now this can be further written as determinant of C multiplying determinant of I minus H minus C inverse of S. Okay, so this is just a manipulation. We're just putting a minus here. And now, what is this expression? So if you look at this expression, so keep this as it is. So determinant of I minus H minus C inverse of S gives what? It gives the characteristic polynomial of the tensor minus C inverse of S, right? So let's do that. So determinant of I minus H C inverse of S will give the characteristic polynomial of sorry, yeah. So this gives the characteristic polynomial of this tensor minus HC inverse of S. So suppose you have a lambda here. This will be lambda minus lambda 1, lambda minus lambda 2, and lambda minus lambda 3, where lambda 1, lambda 2, lambda 3 are the eigenvalues of HC inverse S minus HC inverse S. Okay, so this in place of lambda right now we are having a 1. We have a 1 here. So this determinant of I minus H C inverse S will be 1 minus lambda 1, 1 minus lambda 2, 1 minus lambda 3. So lambda 1, lambda 2, lambda 3 are of the same order as the matrix HC inverse S, which means it is 1 minus lambda 1 plus lambda 2 plus lambda 3 minus Then you have the product terms. So you have plus lambda 1, lambda 2, plus lambda 2, lambda 3, plus lambda 1, lambda 3, minus lambda 1, lambda 2, lambda 3. Now, if you look at the terms, this will be of the order of h, because this is the sum of the eigenvalues of this matrix. So it is like sum of the entries. Therefore, it is linear in h. This will be of the same order as h. This one will be of the order of h square, and this will be of the order of h cube. So as per the definition of directional derivative, these can be dropped. So the directional derivative is the first order term where you are having h. Plus you have certain higher order terms in h square and so on. Those can be dropped. We are only interested in the directional derivative. So we are retaining only the terms with h. So only this will contribute. These are higher order terms. Only this will contribute. Therefore, what it is, the this term is nothing but 1 minus sum of the eigenvalues, but the sum of the eigenvalues is trace of minus h. Sorry, this one is 1 minus trace of minus h C inverse S. So what we started off was C plus HS. We saw it as something like determinant of C multiplied with something else. Now, then we are getting something of the order let me just write it down. So we are getting determinant of C plus HS is equal to determinant of C multiplying something like 1 minus trace of minus HC inverse S. Trace of minus H C inverse S and higher order terms plus higher order terms. So do the multiplication, we get it is determinant of C plus minus trace is linear in its argument, so minus can come out. So plus determinant of C multiplying trace of H C inverse S. H is scalar, so it is determinant of plus some higher order terms. So it is determinant of C plus H determinant of C trace of C inverse S plus higher order terms. Again, what is trace of C inverse S? So trace of C inverse S is nothing but trace of C inverse IK SKJ. So this is nothing but trace of so trace, this is the ijth component. Now trace means you can contract I and j, so you get C inverse IK S KI, but C inverse IK is nothing but C inverse transpose KI SKI. Therefore, this is nothing but C inverse double contracted with S. So what do we get? We get determinant of C plus HS is equal to determinant of C plus H determinant of C, a trace of this, so which is C inverse transpose contracted with S plus higher order terms in H. Now this is what is defined as the directional derivative. So this entire thing is the directional derivative. If you see here, so this is the directional derivative of C in the direction S. This entire thing excluding H is the directional derivative of C, did C in the direction S. So what is this? Now choose S to be dC by dt. in which case we get. So remember where we started? We started with something like this, the time derivative of the determinant, where we are getting dc by dt on the right hand side. Now you choose dc by dt to be s. So we get this thing. There it is. Yeah, if we choose dc by dt to be s, if we choose s as dc by dt, then we get d by dt of determinant of c. This is equal to dou by dou c of zc double dot with, there is this double dot with dc by dt, and this is just s. So what we have on the left hand side now is the directional derivative of determinant of c in the direction s is equal to dou by dou c of determinant of c double dot with s. Therefore, dou by dou, and what is the directional derivative? The directional derivative of determinant of c in the direction s is nothing but this thing, c inverse transpose double colon s. So this is determinant of c inverse transpose double colon double dot s. So it is let c inverse transpose contracted with s. This is equal to dou by dou c of determinant of c contracted with s. Therefore, dou by dou c of I3 of c, which is nothing but the determinant of c, is the same as determinant of c inverse transpose. So we have got the derivatives of the invariants with respect to the tensor c. Next, let us look at a given relationship. Let us derive the stress strain relationship for some for a material for whose stored energy function is specified. So for a Moni-Rivlin material, or let's say this is problem 4. We have a Moni-Rivlin material whose stored energy function is given as W of C is given as C1 I1 minus 3 plus C2 I2 minus 3 plus C3 I3 minus 1 plus K1 log I3 plus lambda times there's a certain function, else it's called WH of J, where J is I3, and I'll just wait 1 minute. Yeah, it is plus lambda times WH of G. Here J is the determinant of the deformation gradient, not C. So this is not I3. That is one thing. Then and in this case we are taking J as this function WH of J is given as 1 by alpha square J cos hyperbolic of alpha into j minus 1 minus 1. So this is the problem. A Moody-Rivlin material is having this potential, which is C1 times I1 minus 3 plus C2 times I2 minus 3 plus C3 times I3 minus 1 plus K1 log I3, where I3, I1, I2, I3 are the invariants of the right Cauchy-Green tensor C. It has an additional term lambda WHJ, but J is not I3, J is the determinant of F. And the function WH of J is given as 1 by alpha square J cos hyperbolic of alpha into j minus 1. This is the format. Now, let us say find the stresses. Find an expression for the, or derive the constitutive relationship. Find an expression for the second PLR Kirchhoff stress S. So let us start. We know that S is given as 2 times rho W, rho C. This is where we started with. Okay. And we also saw it is nothing but 2 times rho W, rho I1, rho I1 by rho C, plus rho W, rho I2, rho I2 by rho C, plus rho W, rho I3, rho I3 by rho C. So, but in this case, we also have a J dependence, which is not I1, I2, I3. We have a J dependence, but J, we'll see what J is. Okay. So J is the determinant of F. I3 is the determinant of C. But what is C? C is equal to F transpose F, which means determinant of C is determinant of F transpose F, which is product of determinant of F transpose, determinant of F. And transpose doesn't affect the determinant, it's determinant of F the whole square, which is J square. So J is equal to square root of I3, which means what is dou J by dou C? It is 1 by 2 square root of I3 multiplied with dou I3 by dou C. So this relationship we can have in mind. So let us have this relationship with us. Now let us differentiate this. So W is given by this function. Let me rewrite that. So I can rewrite the function as W of C is nothing but the first 4 terms are as it is. So it is C1 I1 minus 3 plus C2 I1 minus 3 plus C3 I3 minus 1 plus plus K1 log I3 plus lambda WH of root I3. Fine. Now to get the stresses, we have to do this differentiation. But we have already simplified it a little earlier in the starting of all this. We said using the chain rule, we can write it as this summation. So, so here W is nothing but the psi cap. So dou psi cap with respect to C is nothing but dou psi cap with respect to I1, dou I1 by dou C, dou psi cap with respect to dou I2 by dou C, and so on. Now for this functional, let's find out these quantities, right? So this expression depends only on I1, I2, and I3. There are no other variables. So what is dou W with respect to dou I1? So I1 appears only in the first term, it is C1. Similarly, dou W with respect to I2 is what? I2 appears only in the second term, so it is C2. And what is dou W with respect to I3? So I3 appears in the third term, which is C3. And in the fourth term, so you get a log I3. So you get plus K1. I3 is a scalar. Log I3 is a scalar function. So differentiate the scalar function. So d log I3 with respect to di3 is 1 by I3. So you get a 1 by I3. And then that's it. Then you have a dou I3 with respect to I3 with respect to C. So this term contributes so much. And what about the last term? You get plus lambda. Apply the chain rule. So you get WH dash. W depends only on root J. So it is WH dash of J. And then use the chain rule. So what is the derivative of root I3? Root I3 derivative is we just computed in the previous slide. It is 1 by 2 square root of I3 to I3 by 2. 1 by 2 square root of I3. And here J is equal to square root of I3. So this is fine. We got this. Now what is the next step? We have to find what is WH dash. So WH dash is what? It is dou by dou J of WH, which is, so it's not dou, it is D. WH is a function only of J. So it is D by dJ of WH. And in this case, WH is given by this function. So it is D by dJ of uh, 1 by alpha square cos hyperbolic alpha cos hyperbolic alpha j minus 1 minus 1. Right. Yeah, this is okay. Let's do the differentiation. Use the product rule. So first term, if we differentiate, we get a minus 1 by alpha square j square. And second term, keep it as it is, cos hyperbolic of alpha j minus 1. And now keep the first term as it is 1 by alpha square j. And differentiate the second term. Cos hyperbolic differentiation is sine hyperbolic of alpha j minus 1. Differentiate what is inside the argument. So you get an alpha outside. So the derivative of WH is 1 by, I'll take the minus inside, 1 by alpha square j square, 1 minus cos hyperbolic of alpha j minus 1, plus 1 by alpha square j sine hyperbolic of alpha j minus 1. Now j square is root I, j is root I3, so j square is I3. So have this as it is. So now we have got all the required terms. We got the first W with respect to I1 is there, W with respect to I2 is there, W with respect to I3 is there. Then we got this derivative differentiation. We also differentiated this. And so we have everything that we want. So now put them all together. Right. Also recall these three formula. We got dou I1 with respect to dou C is the identity. Dou I2 with respect to dou C is what did we get? Trace of C, I minus C, and dou I3 with respect to C is determinant of C, C inverse transpose. So this is what we got. Now finally, what is that we need? We want dou W with dou 2 times dou W with respect to dou C. This gives us the stress, which is equal to first term dou W with respect to I1, dou I1 with respect to C. So it is 2 times C1 I. Second term is dou W with respect to I2, I2 with respect to C. Dou W with respect to I2 is C2, and I2 with respect to C is this thing. So we have plus 2 times C2 trace of C, I minus C. Third term. So third term is somewhat big. We have dou W with respect to I3 multiplied with dou I3 with respect to C. So what will multiply? Whatever will get multiplied is determinant of C, C inverse transpose. This will multiply with a big expression. What is the big expression? So the big expression is this thing. C3 plus K1 by I3. K1 by I3 is determinant of C. Then plus lambda by 2 square root of I3 plus lambda by 2 times square root of I3, which is J. Multiplied by WH dash of J. And that is this. Right? That's actually this big expression. So it is what? Oh, sorry, there is an alpha here. So that alpha, there's an alpha here. Let me just, yeah. So there's an alpha by alpha square. Yeah. So that is, that is this expression is 1 by alpha square J square multiplying one by alpha square J square 1 minus cos hyperbolic alpha J minus 1 plus alpha by alpha square J sin hyperbolic of alpha J minus 1. So we can simplify this further. Take so this it's not lambda by 2j plus this lambda by 2j multiplying this entire thing. Right? So lambda by 2j is multiplying this entire thing. Now simplify this further. So S is equal to, and there's a 2 here. There's a 2 here everywhere. So it is 2C1I plus what is trace of C? It is I1 of C. So it is 2C2 I1 I minus C plus 2C3 I3 C inverse transpose, but C transpose is equal to C, which means C inverse transpose is equal to C. So I get an I3 C inverse plus here determinant of C gets cancelled. So we get plus 2K1, right? Plus 2 times K1 C inverse. Plus you have the big, so here you have a determinant of C. Here you have, so we get plus 2. And this 2 and 2 gets cancelled. So we get lambda by, so determinant of C is J square. So I get a lambda J plus lambda J. Here we have the first term is 1 minus cos hyperbolic of alpha J minus 1 divided by alpha square J square plus alpha by alpha square J sin hyperbolic of alpha J minus 1. So this is the final expression for the second Piola-Kirchhoff stress tensor in terms of the right Cauchy-Green tensor C. Let me check the answer. It's 2C1, 2C2 I1 I minus C plus 2C3 I3 C inverse plus 2K1 C inverse plus lambda. You can take the alpha square out. So you get lambda by alpha square 1 minus cos alpha J minus 1 by J plus plus alpha sin its inverse of that. So this expression is fine. So for a Money-Rivlin material, the stress strain relationship is given by this. So the procedure is so there is, I think the first question is similar to this in the assignment 9. Start with an expression. So if it is isotropic, we already have the derivatives of the invariants with respect to C. And then once we have the derivatives of the invariants with respect to C, then use the chain rule. So all that we need to find out is the derivatives of the stored energy potential with respect to the invariants. Then multiply them together, we get the final expression for stress. Next, we can go ahead and yeah, I think this is fine. This part is fine. Next, as the fifth problem, let us look at a compressible Money-Rivlin material. Five point. Yeah, then you can look at the that's not required. So so in the above, in this expression, in the expression derived above, by setting sorry, by setting C1 is equal to mu by 2 and C2 is equal to 0. We recover the constitutive relation for a compressible neo-Hookean material. So in your assignments, the first question is Okay, so C2 is equal to 0, C3 is whatever it is, K1 is still there. Lambda C3 is also set to 0. K1 is, oh, okay, fine. It's okay. So some more things are there. So this, you said C1 is equal to mu by 2, C2 is equal to 0, and then C3 is equal to 0. K1 is equal to minus C1. Yeah. Under these conditions, we recover the constitutive relation for a compressible Neo-Hookean material, which is let me check lambda. Yeah. So I think. Uh, yeah. Okay, anyway, no problem. We can proceed further. So this, by setting this, let's see what we get. So we get first term is C1 will be mu by 2. So we get S is equal to mu by 2. C1I. So mu by 2. So C1 is 2 C1I. So you get a I plus C2 is 0. Second term will not contribute. C3 is 0. K1 is what? K1 is minus C1. So you get a minus mu by 2 into 2 times C inverse. So this entire term has just a lambda plus lambda J. Point 7. Okay, so plus lambda J, this entire thing. Right. So plus lambda J times this entire thing. So this J can take it inside. So you get plus lambda by alpha square plus lambda by alpha square 1 minus cos hyperbolic of alpha J minus 1 divided by J plus alpha sine hyperbolic of alpha J minus 1. So this is a compressible Neo-Hookean material. So the one given in the assignment is slightly different. You have a logarithm squared. So this is a yeah. So this is one example of a compressible Neo-Hookean material. Now let us yeah. So Let me share the full screen so that right. So this is so this stress, this relationship between the Piola-Kirchhoff stress and C defines one compressible neo-Hookean material. The expression given in the this week's assignment is slightly different. So that has lambda by 2 logarithm of j the whole square. So now let us see what are all the characteristics, right? So they have given a deformation mapping. Xi is equal to alpha I capital Xi, where there is no sum over I. Now let us in our problem. So from this Moody-Rivlin model, we have made some simplification. C1 is equal to mu by 2, C2 is equal to C3 is equal to 0, K1 is equal to minus C1. By making those simplifications, we got some other expression for which is a compressible neo-Hookean material. But this compressible neo-Hookean material is different from the compressible neo-Hookean material given in the assignment. So I can solve it, right? So I am not supposed to do the same questions, but I can do a different question that is from the assignment. So here, so neo-Hookean basically means you have a lambda and mu, and here the lambda is multiplying logarithm of j the whole square. So as j tends to 1, this will become this term will vanish, right? If there is if there is an isochoric deformation, this particular component of the stress. So an isochoric deformation will not result in a will have strain energy coming only from the first term. The second two terms will not contribute under isochoric deformation. So in this case, even in our case, we have a compressible neo-Hookean material. If you say j is equal to 1, we get 1 minus cos hyperbolic of 0, which is just cos hyperbolic of 0 is 1. So 1 minus 1 is 0. And j is 1. So this first term vanishes. Second term is sine hyperbolic of 0, which is also vanishes. So if we have an isochoric deformation, this term is not going to contribute. The third term in this expression is not going to contribute. Okay, so let me just write the final expression for this is a different compressible. This is, let me call compressible neo-Hookean material. Let us call this neo-Hookean material 2, or let us call it H2. H2 is given as what? After making the simplification. So this is problem 6. After making the simplification, we have this 2 gets cancelled, 2 gets cancelled. We get mu of mu multiplying I minus C inverse. Mu multiplying I minus C inverse plus lambda by alpha square. Plus lambda by alpha square. So alpha is some parameter. 1 minus cos hyperbolic. J minus 1 multiplying alpha divided by j plus sine hyperbolic of alpha j minus 1. So this is our material model. Now consider a deformation. Consider a deformation. Consider a deformation. Let's say consider a deformation given as x1 is equal to 0, 1 is equal to 0. X2 is equal to this. So this so let us say consider deformation given in polar coordinates. Given in polar coordinates. As follows. So polar coordinates are given by these three coordinates r, theta, and z. So there's an undeformed capital R, capital theta, capital Z. They are going to small r, small theta, small z. Okay. So this is a certain deformation. So so this you can take as capital X1, X2, X3. And this is small x1, small x2, small x3. Now under this deformation, you can consider a deformation given as small r is equal to small r is equal to capital R. Small theta is equal to capital theta plus dz, and small z is equal to capital Z. So so this is a deformation field. So this we are. So the deformation x is equal to chi of x comma t is given by this deformation field at some instance. Okay, so d is a variable. is 1. So now let us find out the stresses. So what is the first step? First step is we have to find the deformation gradient, which is grad of this with respect to the original coordinates. But now the gradient is in the gradient has to be taken in the polar coordinates. So I'll give you the expression for gradient f in polar coordinates. It is, so the gradient in polar coordinates is given as gradient Yeah, in cylindrical polar coordinates, the gradient of a vector is given as dou r by dou capital R, 1 by capital R, dou r by dou capital theta minus small theta, dou r by dou capital Z. Then here we have dou theta by dou capital R, 1 by R, dou theta by dou capital theta, plus small r, and here it is dou theta by dou z. So last one is easy. It is dou small z by dou capital R, 1 by capital R, dou small z by dou theta, and then we have dou small z by dou capital Z. So in our case, if we compute the deformation gradient, what is dou small r by dou capital R? It is 1. Small r does not depend on theta, and so it is, and then you have a minus theta, so it is minus minus b. You get a 1 by capital R. Dou r by dou theta is 0 minus, what is theta? Theta is d is z. And r does not depend on z. Similarly, theta does not depend on r. Theta dependence on theta is just 1. So it is 1 by r, 1 plus small r. Small r is just capital R. And then dou theta with respect to z is d. And if you see, z does not depend on any of it except capital Z. So this is the deformation gradient. Now look at C, which is F transpose F. So F transpose F is 1, 0, 0 minus dz by r, 1 plus r by r. Small theta is what? Small theta is capital theta plus dz. Okay. 1 plus r by r, 0, 0 d1 multiplied with uh, 1, 0, 0 minus dz by r, 1 plus r by r, 0, 0 d, 1. So do the multiplication, we get the result is 1, first one is 1. Then we get minus dz by r. Then we get 0. Second term we get 0. This is 0. So no, wait. So this is minus dz by r. It is symmetric, minus dz by r. So this will be d square z square by r square. D square z square by r square plus 1 plus capital R the whole square by r square. Then this term will be dz by r, d into 1 plus capital R by r. So this is just one term. And the third row we get a 0. So this was the symmetric. So this is d into 1 plus capital R by r. The last term will be d square plus 1. So this is our C. Now, is the deformation isochoric? So let us say J is equal to determinant of F. What is the determinant of F? We can expand about the last row. So if we expand about the last row, we just get. We check the. C theta. So it's. Okay. So then. So the determinant of F is 1 plus capital. So this you can expand about this row. So it is 1 plus R by capital R. So it is 1 plus R by R. So this deformation is not isochoric, and uh, So the trace of S will be look at the first part. So trace of S, the first one will contribute mu. So this first expression will contribute a 3 mu minus 3 times trace of C inverse plus lambda by alpha square. This is a oh yeah, there's a C inverse multiplying this, so there is also a C inverse here. It's a C inverse. Right, so okay, from this point, let us take it up in the next class. Okay, so this we are already out of time. So given a deformation gradient, first this procedure is find f, then find determinant of f. See the j part. If it is equal to 1, you can say some parts will not contribute. Some parts of S and W will be 0. Then you see C. From C, you can get the invariance I1, I2, and I3. Once you get them, you can directly get the stresses. So yeah, since we are late, we are already late. I'll stop the session here. I'll share the file because too much has been written today. I'll save it and then I'll upload it on the folder. So if you have any doubts, you can write to me because I have not completed it. You can write to me. I'll clarify. So let me stop recording here.